Okay, great. So welcome back, everybody, and we will continue with the second session on testing general relativity by Professor Paolo Pani. As usual, if you have any questions, you may either type the question in the chat and I will read it out. Alternatively, you can raise a hand and ask the question yourself. All right, over to you, Professor Pani.
Okay, thank you very much and welcome back. So today's lecture will be about gravitational wave-based test of gravity. The first of the two lectures, also tomorrow, will be devoted to this topic. But before going there, I want to just close the overview that we had yesterday about so-called classical or weak field test of GR, also to introduce a novel effect that we didn't discuss yet, which is the one related with the spin. So when a spinning body in GR drags the space-time around it, producing novel effects that we didn't discuss yet. So this effect is usually referred to as frame dragging, because effectively the object drags the frame, the reference frame of observers attached to it, and it can be studied by considering a weak field expansion of the metric that can be written in this form. The leading order term is the Schwarzschild correct, the Schwarzschild term expanded on large distances. So here it will be a 2 minus r with r squared. Of course, there will be higher order correction that I'm not writing, and then there is a 4jr square theta let's see if I put the sign fine. Okay, so this metric is the large distance expansion of the Schwarzschild solution plus this extra term that we can call a gyromagnetic term, and is an off-diagonal term that depends on the phi t component, and in this weak field expansion, m is the total mass of the space-time, while j is the angular momentum. And in the g equals 1 unit that we are using, j over m squared is the dimensionless quantity that for a Schwarzschild, for a spinning black hole, the Kerr solution is bounded between 0 and 1. But in general, well, no, okay, forget about it. Okay, so this metric here, this diminutive metric, can be written as a Minkowski background plus some corrections, h mu, which encode both the effect of the mass and the effect of the angular momentum. And what one can study in this geometry is how a gyroscope, so a point particle with an intrinsic angular momentum without any external torque acting on it, would move, or would anyway change its intrinsic angular momentum. And this can be studied by considering essentially the fundamental equation for a gyroscope in spatial relativity. So considering a local inertial frame, the equation for a gyroscope tells us that the intrinsic force spin parameter, S mu, is constant in terms of the proper time of the particle. This is valid in a local inertial frame and can be written in general, in a general frame in this form, where the symbol here is the covariant derivative already introduced yesterday. Oh, sorry. So this is the equation that is valid in any reference frame. And another relation which is valid is a scalar relation, and it's valid in any frame, is the fact that this vector here, this core vector, is orthogonal to the particle for velocity. So then one can solve these two equations that will give you the dynamics of this spin for vector in a generic space-time. In particular, one can study what happens in this weak field expansion of a spinning geometry. And the final result is the following. Let me write it. What one gets. Of course, this is a scalar equation that can be used to solve, for example, for S naught, the time component, and then plugging this back here, we reduce this to an equation for the 3 component of the vector, and the final result is the following: that ds 3 vector p tau is equal to omega vector product S, where this omega can be written in this form. Where a comma is partial derivative, this is the Levi-Civita tensor, is totally antisymmetric, and is the k component of these 3 vectors. So what this equation tells us is that whenever we have this omega to 0, and we have omega to 0 when we have some off-diagonal component of the metric perturbation, so when we have this term here, the spin 3 vector is not constant along the proper time. It changes according to this equation here, and this effect is called precession, because effectively the spin is preceding, and is due to a coupling between the spin, intrinsic spin of the particle, and the angular momentum of the space-time. So it's a coupling between this J here that appears here and the spin of the particle, and this is due to the fact that the angular energy, essentially, the rotational energy of the body gravitates because it produces, it has its own stress energy tensor. If one works out the final expression for this omega, let me write it here. The result is the following: is 1 over r cube is really just obtained by plugging the metric inside this formula, and what one gets is this expression. J is the angular momentum vector, x is the vector position of the particle, and one gets this result here, which is called length theory frequency. And is due, is responsible for what is called length theory precession. So the effect is the fact that the spin of a gyroscope in a rotating space-time precedes with a frequency given by the absolute value of this guy. If we consider the case in which J is orthogonal to the position vector, so the star product is 0, what we get is that the absolute value, what I can call length theory frequency, is simply restoring the physical unit Gj divided by c squared r. So it's a small effect, both because it's linear in the spin, and this quantity can be generically small. For example, if one thinks about the sun on the Earth, they are not rotating very fast. And also small because it decreases with the third power of 1 over r, meaning that at large distances, the frame dragging effect is less important. And of course, it's less important than the potential given by the mass that instead goes like 1 over r. This is only part of the story for the precession of a gyroscope, because there is another effect that is purely relativistic. In fact, it does not have to do with the spin of this object. It's called the Sitter precession, and it's another term due to the fact that a spinning particle in a curved space-times, if it moves, so if it doesn't move, so if it is at rest with respect to this reference frame, this will be the only effect. But if it moves, there is another correction that is called de Sitter, or also sometimes geodesic precession. And this effect is not related with the spin, with the particle spin, but has to do just with the mass of the space-time. And here is the expression. Okay. So these are the two frequencies which are relevant to understand the precession of the spin vector of a particle moving in a curved space-time. This effect is proportional to the spin of the space-time. This effect is not. And in fact, this is typically more important than this. The reason is twofold. One is that this becomes arbitrarily small when the spin is small. The other is that, as you can see, the power of R here is smaller than here, meaning that this effect survives, I mean, it's dominant at larger distances. And when one considers a gyroscope in a curved space-time, one has to consider both effects, which might be of the same order, or maybe this would be subleading. The effect of frame dragging is being finally measured by the gravity probe B experiment in 2011, if I'm not wrong, after many years of understanding the data that has been taken. And it was the first measurement of both effects, so the geodesic precession and the lens steering precession. While this effect only has been detected also in the past through pulsar timing and other effects. And again, this was a confirmation. It's not a particularly precise measurement because it's hard, and also spin effects are hard to measure. But it is another confirmation of generativity in a totally different sector, because so far we probed only this part of the metric. This is still a kinematic test, because we are probing effects on geodesic motion and not dissipation and energy emission, but it's still a confirmation of generativity, orthogonal to the others. Another relevant point is that very recently, the lens steering effect has been also measured for the double partial system that I mentioned yesterday. So in the paper I referred to yesterday, Kramer et al. 2020, no, sorry, 2021, just 2 weeks ago. They reported, so these radio astronomers reported the first measurement of the lens steering effect in a binary pulsar. And this was a major achievement, first because it proves this effect in a totally different setup. Gravity Probe B was a satellite around the Earth. So the space-time, of course, is almost flat because the Earth is not very compact, while around a neutron star things are very different. And also it's important for another reason, because for a pulsar, one can measure independently omega, the angular frequency, and through the lens steering effect, one can measure J, the angular momentum. And this is important because the omega is related to leading order through the angular momentum through the moment of inertia, capital I. So having an independent measurement of omega and J allows to estimate the moment of inertia of neutron stars, which is particularly important because this depends on the equation of state. So it's a way to measure the equation of state of neutron star and put some constraints. Constraints so far are not that stringent. The reason is that these measurements are tough and not very accurate, but as a matter of principle, it's interesting that by measuring the angular momentum, one can try to constrain the so far not totally known equation of state. Okay. So if there are no questions so far, yeah, no, you have the
Professor Pani, actually, I do have a question here.
yeah.
Yeah, I was wondering whether these expressions for the different frequencies of the precession, are they valid only for equatorial orbits, or would they also work for inclined orbits?
Let me see. I would say so I should check the derivation because if I'm not wrong, the derivation I was following, that is also one of the references I gave yesterday, is generic because, well, I might be wrong here, I'm not sure, but I think that the derivation is based putting ourselves in a reference frame centered around the big object, so the spinning object. And therefore, the position of the gyroscope is identified by this quantity x, and it can be generic. So these terms account for the possibility that the object is not located orthogonally to the angular momentum of the object. So the setup is something like that. There is this object with angular momentum j. This is the equatorial plane. This is x, and there is here a gyroscope spinning along some direction. In the particular case in which j and x are orthogonal to each other, one reduces to this simple form, otherwise it should be generic. An important point is that this does not require, I mean, it's an effect that would be true also for a static source. It does not require the source to move. This effect is geodesic, so it's assuming an object in orbit, and in fact I think it assumes also equatorial orbit. But this one does not need any orbit. I mean, it's an effect that is also true for static sources.
I see. Thank you.
Sure. Okay. Yeah. The last thing I want to mention, also because it's relevant for what I'm going to say next, is that everything we said here was about point particles and geodesic motion. One could argue that for neutron stars, this is not very consistent because, well, for example, if we take a satellite around the Earth, of course, the mass ratio is very either large or small, if depending on how you define. So if we define the mass ratio as m2 divided by m1, where m1 is the big guy, typically the mass ratio is much smaller than 1 for weak field tests, and so the geodesic approximation taking a point particle is well motivated. For pulsars, for double pulsars, this is not true anymore because pulsars have the same mass, so q is of order unity, plus the orbital velocity is mildly relativistic, especially for these systems here that is particularly relativistic. And what I said for point particles and geodesics does not directly apply to pulsars, at least precisely. It might apply as an order of magnitude, but for pulsars and for objects with comparable masses, one has to go beyond the geodesic approximation and study what is called Prospectorial Theory. That is an expansion of Einstein equations in powers of the orbital velocity divided by the speed of light. And this is what I will also discuss now by introducing gravitational wave-based tests. So,
Professor Pani, we have a question here on the chat, so I'm just going to read it out to you. Can you explain again the difference between geodetic precession and lens-theory precession?
okay, so the lens-theory precession is due to spin angular momentum coupling. So it's the fact that in GR, of course, in Newtonian gravity, an object, if it's spinning or not, it does not affect the way it interacts with other objects. In GR, this is not true anymore, and because of spin angular momentum coupling, there is an effect on the motion of the intrinsic spin of the gyroscope, which is given by this term. The geodesic precession instead is different. It's something that would occur even if the if the Earth, for example, was not spinning, and in fact there is no angular momentum here. And this is just due to the fact that the spin vector, when it moves in a curved space-time, it also gets a non-trivial contribution due to the mass. So in flat space-time, this will be zero, there will be no correction. In a curved space-time, even if the object is not spinning, there will be a correction due to the curvature. So conceptually, they are two very different effects, but they are competitors. And in fact, it happens that this guy is bigger than this other, but the length steering effect is crucial to measure the spin. So somehow the effect is buried in this dominant effect. Okay, so let's move now to the main topic of today's lecture. Actually, this will be the main topic of today and tomorrow's lecture. And today I will focus on mostly on spiral-based test of gravity. And I will also, give some background for granted, because I'm sure that also in the lecture that you had this morning, you are covering the basic aspect of gravitational waves. So I'll just try to recall the ones that are needed here. But the crucial point is that for binary systems sufficiently close to each other, we can model, the goal is to model what is called the coalescence, so the fact that the two objects emit gravitational waves, approach each other, merge, and form possibly the form black hole that vibrates. And these different phases, the spiral, the merger, and the ring down, potentially can be used to test different aspects and different sectors or of many different fields. So today I will focus on the spiral mostly, which is the initial coalescing phase when the two objects approach each other by emitting gravitational waves. Tomorrow I will mostly focus on the merger and the ring down, especially. So the final phase of the coalescence and the post-merger phase. So for today, I will focus on the spiral. And so a crucial point to understand is that at variance with the tests that we have seen so far, these are dynamical tests, in the sense that the sources that we are probing are dynamical. It's not just geodesic motion. We are really studying how energy is emitted through gravitational waves. And in fact, they tested two different sectors, which we could call the conservative part of the dynamics and the dissipative part. And depending on the theories, these sectors can be both affected, one can be affected, the other cannot, etc. And in fact, they are conceptually very, very different. The way the spiral can be studied is through post-Newtonian theory, and I can refer to, for example, Poisson and Will's book on this, which I think is an excellent account for the basics and also the more advanced, some advanced application of post-Newtonian theory. And the idea is to solve Einstein equations, as I was saying before, in an expansion when the orbital velocity v is much smaller than the speed of light, c, and the typical order expansion parameter, which in fact counts also the Pn order of value terms, is the dimensional ratio of the squared over c squared. So let me actually go back for a moment to what we said yesterday. So yesterday we introduced the PPM formalism, parameterized post-Newtonian formalism, and the idea was to parameterize the metric, for example, G naught naught, was written as -1 minus 2m over r plus, or well, maybe it was a minus, but anyway, it doesn't matter, m squared over r squared plus first, where here these were parameterized post-Newtonian parameters, and the crucial idea of a parameterization is to introduce terms which are possibly numbers, so dimensionless quantities, that can be used to map the generic parameterization into a given theory. And this is very convenient because if we can do that for many theories, we can study the parameterization, put bounds on these parameters here, and then a posteriori map these parameters into those of a given theory and constrain the theory once and for all. So we don't need to work out the computation for each theory, but it's sufficient to just work at the level of the parameterization. For a binary, the most relevant test of gravity that one can do relies on a very similar idea. So one wants to parameterize in a certain way observables that in this case for a binary would be gravitational wave signals, and introduce extra parameters that can possibly cover all corrections to GR and put constraints on those parameters. So how do we do that in post-Newtonian theory? Well, the idea is to work out a generic signal. So the signal in GR would be written through the two polarization of gravitational waves, the plus and cross polarization as an amplitude, and then there will be a phase that we call e to the I phi dw, and this is the phase. And we want to find the post-Newtonian expression of the amplitude and phase, which would be essentially a series in these in powers of this post-Newtonian parameter, roughly. And then the idea is that we will deform that expansion, introducing extra coefficients that would be, sometimes they are called parameterized post-Einsteinian coefficients that can be used to constrain the theories. So before going there, let me give you a 5 minutes overview on how to write down frequencies and amplitudes, essentially in GR, starting at the leading order, if you want, post-Newtonian level, which would be just Newtonian gravity. So the leading order term in this expansion. And the idea is that one can start with a Lagrangian for the two-body system. And let me write this Lagrangian, let me write it properly. Let me write this Lagrangian in terms of reduced mass mu. V is the orbital velocity, and this is mu m over r. So let me write some notation. Capital M here will be the total mass of the system, and 1/2. Mu is the reduced mass, so it's M1 and 2 divided by M. And later on, I will also introduce mu, which is mu divided by M, the symmetric mass ratio. And we can also define the mass ratio Q and 2 divided by M1. And it is smaller than that. Okay, so this is the Lagrangian for two-point particles with mass M1 and M2 orbiting each other, interacting only gravitationally. From this Lagrangian, one can compute, so this Lagrangian in general, for the system would depend on the relative position R. It can depend on the velocities, let me call it di and xi. It can depend also in principle on the acceleration. So now Lagrangian and Hamiltonian mechanics tell us that given a Lagrangian for a conservative system, so a system that is not losing or gaining energy, we can compute the energy of the system. Okay? So there is a standard procedure, essentially a formula that relates the energy of the system through derivatives of the Lagrangian. Actually, I can write you the general formula, which might be relevant in some context. Although we're not going to do the computation, but okay. Okay, so this is the generic expression that one can compute in Lagrangian mechanics to compute the energy of the system given a Lagrangian. And this will be valid in general, even if this Lagrangian is then complicated by extra post-Newtonian terms that we will see in a moment. But so the idea is that given the Lagrangian of the system, one can compute the energy, and this energy is essentially the equivalent of Kepler's law in Newtonian gravity, but can acquire corrections in this expansion here. And so this describes the conservative part of the dynamics. So how the energy of the system is related with, for example, the orbital radius. The second part of this computation is given by the fluxes, which tell us how energy is emitted, is lost in the system through the emission of gravitational waves. And to leading order, one can use the famous, what is the Greek factor? The famous quadruple formula, which relates, this is the flux, so this is E dot GW, energy emitted per unit time, and relates this to the third derivative in time of the total quadruple moment. This is the quadruple moment of the system. So this is a quantity that can be computed in Newtonian gravity. If I take an orbit, a two-body system with a given orbit, say circular for simplicity, I can compute the quadruple moment of the system. From the quadruple moment, I can take the third time derivative, contract these two guys here. This is a scalar quantity that tells me the flux, so the energy needed per unit time. And this is true in to the leading post-Newtonian order. It's suppressed by a factor 1/6 to the 5, so it's a small effect in principle, but it's nevertheless present. And of course, there are also corrections. For example, order 1/c to the 7, which, for example, depends on the contraction EIJK, where this guy is the octuple moment, and so on and so forth. So one can consider all possible contributions to the fluxes to any post-Newtonian order coming from all possible multiple moments of the system. Okay? But anyway, the point is there is a prescription to go from a given orbit defined by the conservative part, and how much energy per unit time is emitted for that particular orbit, given the multiple moments of the system. So and this guy is of course describing the dissipative part of the dynamics. So in general, if I call this, I can introduce a quantity, let me maybe raise here. I can introduce a quantity, let me call it x equal to m omega. Omega is the orbital angular velocity to third, and this is v 1/3. This is the orbital velocity, this is the angular velocity. And this quantity x must be much smaller than unity, in order for post-Newtonian theory to apply. So if I take this Lagrange and I start adding post-Newtonian terms, and I do the same for the flux, it turns out that the energy is essentially schematically a series with some coefficients depending on this x to some power. Let me call n. Where I can compute the coefficients order by order in this expansion. Same thing for the flux. Also, the flux will be the sum with some other coefficients to the power of xn. There are also, well, I'll discuss them in a moment. There were also possibly logarithmic corrections, so this is not a really tailored series to all orders, but schematically something like that. And why this is important? Because if one has the fluxes and the energy, essentially through an adiabatic approximation, one can compute how much the, essentially one can compute the gravitational wave phase, and the way this can be done is by saying that if I take this E, the E dt, the change of energy, the adiabatic change of energy of the binding energy of the system will be minus compensated by the flux. And if I take this equation, this is essentially an equation of motion that I can solve for the orbital distance, for example. So it tells me how the orbital distance changes in time due to the emission of gravitational waves. Finally, if I have this quantity, I can compute how the orbital frequency, which to Newtonian order is just the Kepler's law, how the orbital frequency changes in time, and we know that the gravitational wave frequency is just twice the gravitational wave. The gravitational wave orbital frequency is twice the orbital frequency itself. This is due to the quadrupolar nature of the waves. If I know the gravitational wave orbital frequency, this is actually the derivative, the time derivative of the phase. So you see that conceptually, we have all ingredients to compute the gravitational wave phase, because if I know this coefficient, x depends on omega, which depends itself on the radius. If I know the fluxes, this is a differential equation for the orbital distance, therefore I know the orbital frequency, therefore I know the gravitational wave frequency, and finally I can solve for this equation to get the gravitational wave phase. Okay? So all of these to motivate this formula, this schematic formula that tells you that the gravitational wave phase, let me see. Well, let me write first the leading order Newtonian term, which I'm sure you already discussed in this morning lecture. But so to leading Newtonian order, the gravitational wave phase depends on a given coefficient, remember? And to some power of this parameter x, in particular x to the minus 5/2. And in fact, it depends on what is called shear mass, which is mu m 5. And this can be seen by restoring the various terms, mass ratio and the total mass and here. So this shear mass is the crucial parameter that describes the gravitational wave phase. This is just the leading order. In fact, if one computes the post-Newtonian corrections, there would be corrections to this formula here. And in general, one can write the gravitational wave phase, and this is what is relevant for me now, in this form. Okay. and this is what I want to discuss now. So in general, schematically, if one extends what I just, this procedure that I just explained to higher post-Newtonian order, which might become trivial because one has to consider all possible multiple moments of the system, all possible couplings in the Lagrangian, etc. Nevertheless, the schematic form would be something like that, where there are these coefficients here, which are just numbers that depend on the system. So they will depend on parameters like the intrinsic parameters of the binaries, the masses. So let me write alpha n would depend on the two masses, mi, 1 and 2, the two spins, chi I, where I will define chi I as ji divided by mi squared, so these are dimensional as quantity, and these are vectors, in fact. And well, they can depend on the coalescence time, the coalescence phase, plus anything that is beyond jar that we will now discuss. So of course, in GR, these coefficients depend really only on masses, spins, and other parameters of the binaries, plus corrections that depend, terms that depends on the position of the binary. And if the objects are black holes, because any black hole in GR is described just by the mass and the spin, there is really no extra parameter. So it's really everything depends only on masses and spin vectors. The idea is that in this form, this is a serial expansion in this parameter gravitational frequency, which in fact is related with this x, and it gives us a hint to construct a parametrization in which we deform these parameters by introducing corrections. So the simplest thing one can do is say alpha n is equal to alpha n gr plus some correction. Let's call delta alpha n that will depend on the OGR step. Okay. And these parameters will play the same role of the parameterized post-Newtonian parameters for a static metric. Here instead they will define the full gravitational wave phase. And notice that this number alpha n here are a combination of these coefficients and these coefficients. So there is a mixture between possible corrections coming from the conservative part of the dynamics and those that come from the dissipative part of the dynamics. So essentially, if a theory, for example, does not modify gravitational wave emission compared to general relativity, the fluxes will be the same. What will change is maybe the conservative part. So, for example, Newton's law and the way orbits are related with the frequency, for example. And the corrections to these coefficients here will enter these alphas in certain way. The opposite might also be true, that maybe the conservative part of the dynamics is the same, but the way gravitational waves are emitted is different, maybe because of extra degrees of freedom, for example, extra polarizations. I will discuss this in a moment. And therefore, the fluxes are different, and nevertheless, correction to the gravitational wave phase might be present. Let me also mention that because of back reaction effects in the post-Newtonian series, there is also inside here terms which I would call plus log d terms. So there are terms that depend also on the logarithm of the orbital velocity. They are typically submillion with respect to others, but nevertheless present. So this series is important to keep in mind that it's not a Taylor expansion. There are also logarithmic corrections, but other than that is the full story. It's the full story, of course, in this regime here, when the velocity is small. When the velocity is not small anymore, which is something that is broken near the merger, the post-Newtonian theory does not converge anymore. And in fact, it does not converge well even in this regime when Q M2 divided by M1 is much smaller than unity. The post-Newtonian theory converges very poorly, and this regime is relevant for what is called extreme maturation spirals or engines. These are not sources for current detectors, but will be sources for future detectors. And the spiral of these guys is very relevant because actually in this mass ratio, the secondary object can make several orbits. I mean, a huge number of orbits around the primary object. So essentially, it can probe both the geodesic motion and gravitational emission very accurately. But post-Newtonian theory for these objects is not the best approach. What one can do is to solve both the geodesic motion for a test particle and compute flux is not in the post-Newtonian expansion, but using black hole perturbation theory. And I'm sure that you will learn more or are learning more during Eric Poisson's lectures on black hole perturbation theory. So this is just to say that post-Newtonian theory is well designed to discuss small velocities compared to the speed of light and mass ratios which are not too far from unity, or anyway they are not incredibly small as in the extreme maturation. Okay. So now let me focus on this correction here and I will cancel the rest.
Professor Pani, I have a question here.
Sure.
So the flux balance equation that you had put down, if I understand correctly, that's valid in the adiabatic approximation, if I'm not mistaken. Could you comment a little bit about that? Why it's only valid in the adiabatic approximation, or if I'm misspeaking here?
Sorry, I didn't understand. In the adiabatic approximation, you asked?
Yes, I'm one. So the flux balance equation, dE by dt equals minus E dot, right? That's valid in the adiabatic approximation. I was just wondering why that is the case. I would have thought that a flux balance equation is a general conservation of energy equation, but why is it only valid in the adiabatic approximation?
Right. So so let's see if we can do it quickly. So the idea is that that approximation is valid whenever the energy flux, I mean the time scale related with the energy flux is small compared to the typical time scale of the system, for example, the orbital time scale. In order to estimate this, let's see, one can say that the time scale, let me call it for radiation reaction, tau r, is E divided by E dot dw. So this is a time that tells us the time scale over which the energy is changing due to gravitational emission. And on the other hand, the orbital time scale is well, it's just 1 over omega, 2 pi 1 over omega, which is 2 pi r cubed divided by m. If one compares these two quantities, it's easy to see that at large distances, this guy becomes very large, while this guy decreases. So when x is much smaller than unity, tau radiation reaction is much longer than tau is much smaller, sorry. Much larger than tau orbit, which essentially means that during a certain number of orbits, we can take the radiation reaction term to be constant, and therefore apply an adiabatic approximation. So there is a separation of scales due to the fact that these two guys are very different from each other in the post-Newtonian regime. Again, this is broken when the velocities are large, and this separation of scales is not valid anymore, but at least at large distances is a good approximation.
I see. Thank you.
Okay, so let me keep this formula here. So now I want to discuss which kind of corrections should we expect from this formula here, depending on the theories and depending also on the sources that we want to consider. So let me start well with the first one, maybe one of the most important ones, which is dipolar radiation. So we know that GR is a quadrupolar theory, and this is why the flux formula, the quadrupole formula I was mentioned before, tells us that two leading order fluxes are given by quadruple, the derivative of quadruple tensors. But it does not need to be the case. If there are extrapolarizations in alternative theories, there might be dipolar radiation. So there might be a scalar mode, for example, that will produce dipolar radiation. So dipolar radiation, being a dipolar term, enters at order -1 pn compared to the leading order Newtonian contribution. What does this mean? It means that in this formula here, there is a term that goes like 1/v². Correct. Okay, so there will be 1 plus, this is Newtonian. And then there is a term with some coefficient, let me call it beta. And this goes like 1/v². So it's a term that potentially, because it's negative in order, becomes dominant at large distances, which is what you would expect, because the larger the distance, the more important will be the dipolar contribution compared to the quadrupolar contribution. Of course, this beta coefficient encodes the deviation from GR. So the fact that in this theory there is some charge that produces the emits this dipolar radiation. So the simpler case one can think of are scalar tensor theory. That, as the name goes, are theories in which there is a scalar field coupled to gravity. So the gravitational sector is also mediated by a scalar field. And let me write just as an example, so, I mean, to give you some flavor of this theory, the action for the simplest of them, which was historically very important, so-called Brans-Dicke theory. And this is the following. So there is a scalar field phi coupled to the Ricci scalar. There are some couplings, kinetic couplings, parameterized by this function omega phi that are coupled to the kinetic term of the scalar field. And then there can be a potential. Okay, and typically the matter sector here depends on some field, let me call it psi, and is coupled to the metric field, minimal coupled to the metric. Okay, so this is called Brans-Dicke theory. Actually, Brans-Dicke theory is without a potential, but doesn't really matter. This is the standard expression. Because matter is minimally coupled to the metric, to the standard metric, this theory satisfies the weak equivalence principle that we mentioned yesterday. So there is geodesic motion, which is evident here in what is called Jordan frame. However, it is possible to make a field redefinition, so change the field phi and some of the function here, and transform this theory, I will write it down, in an equivalent form, it's totally equivalent, and well, let me write actually that transformation. So if you write a new metric, let me call it G mu nu bar equal to A minus 2 of phi G mu nu. And then you write A of phi equal to 1 over more phi, and these, let me see, we introduce 3 plus 2 omega phi equal to 1 over alpha squared, where alpha is the log A phi. Okay, so there are a series of transformations. Basically, you introduce this function alpha, which is just related with omega, entering the kinetic term. Then you introduce this function A that is related with alpha through this logarithmic derivative. The new field phi, bar phi is related with phi through this relation. And you make a conformal transformation that relates the matrix G mu nu and G bar mu nu through this formula. I leave as an exercise to show that this action here transforms in the following way. This is the determinant of G bar. This is the Ricci scalar bar of the bar matrix. This is minus 2 G bar mu phi the new field minus a new potential mu phi, plus a matter term that depends on a squared phi. Okay. So these two actions are equivalent to each other because we just redefine the fields, and this is called Einstein frame. So what is the difference between the two? In the Jordan frame, the field and matter are not minimally coupled, but the field and gravity are not minimally coupled, but matter fields are minimally coupled to the metric. In the Einstein frame, gravity and the scalar field are not coupled to each other. These are minimally coupled scalar field, but matter does not see the standard metric. It sees a conformal metric defined where also the scalar field enters. Okay. Depending on the situation, it's more useful to use one or the other. For black hole binaries, this one is simpler, much simpler, because black holes are vacuum solutions to GR, so there is no such a term. And as you can see, if there is no matter, so this term is 0, then the theory that you get is essentially GR plus a minimally coupled scalar field. And for these theories, there are several what are called no-hair theorems. Let me write right here. So these theorems tell us that in a theory like that, under certain very mild assumption of the potential, black hole solutions in this theory must be the same as those of GR. So essentially, it's a way to show this theorem prove that black hole solutions in these theories are exactly the same as GR. In particular, they do not have any scalar charge. In principle, they could have some quantity that is related with a scalar charge, so they can be sources for the scalar field. But it so happens that in many of these theories, in these scalar tensor theories, this does not occur. Which unfortunately means that for black hole binaries in these theories, this dipolar emission is exactly zero. So there is no dipolar emission, not because the effect is not present, just because this beta is zero, because the scalar charge of black hole is zero. What I just said is not true anymore for neutron stars. For neutron stars, there is matter, so there is a fluid. This term is not zero. And in fact, if one works out the field equation for the theory, the final result is the following. I will write it because it might be useful. Is the following. So this is the field equation for the scalar field. Box phi, phi equals to minus 4 pi alpha phi d bar, where by bar I mean quantities evaluated in the conformal metric. And you see, if alpha phi equal to 0 is not 0, so of course it depends on this coupling constant here, which eventually depends on this guy and of omega. But if alpha of 0 is not 0, then phi equals 0 is not a solution of this equation. This is the trace of the stress energy tensor. So for a neutron star, this guy is not 0, is roughly given by the density of the fluid. And for any theory in which this function alpha is not 0 and alpha equal to 0, alpha equal to 0 is not a solution. Sorry, phi equal to 0 is not a solution. So this tells us that whenever we have matter in scalar tensor theory, we also have a non-trivial scalar profile, and in particular it can be shown that neutron stars, or whatever stars, generically, in these theories, might have scalar charge, so they might have an extra parameter that tell us how much scalar field is sourced by these neutron stars. And in fact, for neutron star binaries, this beta is not 0. In fact, it happens that this beta is proportional to the difference between the two charges. So if the neutron stars have exactly the same charges, this term is 0 because by symmetry there is no dipolar emission. But if the charges are different, this guy is not 0. One can put constraints on the -1 p.m. So what has been done among the various tests performed by the LIGO collaboration is to deform these parameters, introducing different post-Newtonian corrections, for example, -1 p.m. corrections, or corrections to the leading order post-Newtonians, 2 p.m., etc. And I can refer to this paper here that recently appeared in December. So this is the most updated paper about test of gravity with the current catalog of transient events, GWTC3. And there you will find a complete overview and results about the various tests of gravity that the LIGO collaboration is performing. And one of them, one of the most important ones, is precisely to find posterior distributions for corrections to these parameters here. Sometimes the corrections to these parameters are called parametrized post-Einsteinian corrections, sometimes are called phenomenological spiral model. But anyway, by introducing them and then try to constrain them to the data, I want to put constraints generic on these parameters, potentially on a given theory. For example, in this case here, if one puts a correction to the -1 p.m. term, automatically that can be translated into a constraint on the scalar charge of neutron stars. For binary black holes, of course, this term is 0 in this theory. This is not always the case, in fact, because there are other theories, for example, those that I mentioned yesterday, in which the Lagrangian is, say, R plus some coefficient R squared plus beta, alpha, beta, etc. These are different theories. It's typically called quadratic gravity. And something interesting happened here in these theories. Actually, a typical example of this theory is the following. Is what is called Gauss-Bonnet gravity, when this term Gauss-Bonnet is R squared minus 4 R mu plus R mu rho sigma R mu rho sigma. So it's a particular combination of the three quadratic curvature invariants, and this is called Gauss-Bonnet gravity. Particularly interesting for various reasons. One is that, well, as it stands, this term does not contribute at all to GR because it's a total derivative. It can be shown to be a total derivative. So this theory gives the same equation of motion of general relativity. What typically is done is introducing a coupling to a scalar field that is inspired by some high energy extension of relativity, in particular in string theories there are couplings of this term. And a theory such as this one plus a kinetic term for a scalar field is called Einstein scalar Gauss-Bonnet gravity. And it has some interesting properties. In particular, if you compute the field equation for tau phi, you get something like this, schematically. Okay. So it's a form, I mean, it's a schematic form similar to what I showed in scalar tensor theories, but here the source term of the gradient of the D'Alembertian is not the trace of the stress-energy tensor, but is the Gauss-Bonnet term. Why is this really interesting? Because, for example, for a Schwarzschild black hole, the Gauss-Bonnet term is not zero. And therefore it tells you immediately that whenever f prime of phi computed as 0 is non-zero, the Schwarzschild solution with zero scalar field is not a solution of this theory. So this is a simple way to show that at variance with scalar tensor theories, in quadratic gravity, typically black holes are different from general relativity because they acquire a scalar pair. So this is an example of violation of the D'Oehr theorems for certain theories, which predicts black hole solutions different from GR. There is a large class of these theories that might modify black holes both when they are static or when they are spinning, introducing some certain term that violates parity. And I mean, of course, they have different phenomenology, but overall, these corrections modify both the metric of a black hole and also the gravitational wave emission, because clearly a different theory in general produces different fluxes. And in this case, for example, in both this case and in scalar tensor theory, there is a scalar degree of freedom that contributes with bipolar emission. So in both cases, we can compute the fluxes, the conservative part of the dynamics, and for each of these theories, we know this the corrected version of this expression here with the proper parameterized post-Einsteinian corrections. By the way, for the PP corrections, parameterized post-Einsteinian, I can suggest this paper by Younes and Pretorius in 2009, I believe, where they introduced precisely this parameterization, which is called PPE or parameterized post-Einsteinian correction. So the upshot is that the scalar tensor theories and quadratic gravities are sort of complementary to each other, because in scalar tensor theories, black hole solutions are the same as GR, at least in these theories here. In quadratic gravity, black hole solutions are different from GR, generically. Neutron star solutions are the same as, are different from GR. They have scalar charge in scalar tensor theories. While in quadratic gravity, it can be shown that precisely because this Gauss-Bonnet term is a special term in the theory, neutron stars do not acquire scalar charge. So they are really orthogonal in terms of which one between neutron stars and black holes acquire scalar charge, and therefore acquires a -1 plane correction. Okay. So this was just one example of correction of the gravitational wave dynamics, but there are many others. For example, one can consider a variable capital G, so elevating the G to some function of space-time. This is relevant in certain cosmological theories in which essentially they advocate the gravitational coupling is not the same through time and also through different places of space-time. And these theories introduce a -4 Pani correction. And as you can imagine, they are very well constrained by systems at large orbital distances, because a -4 Pani corrections contribute mostly when the velocity, the orbital velocity is very small. Of course, this is just the leading order, because, for example, the scalar tensor theory I mentioned before and other theories starts modifying GR at -1 Pani term, but then they modify the whole tower of Pani corrections. So in fact, for a given theory, we just don't have one single parameter. We have many parameters, all related to each other into the fundamental constants of the theory, but that they potentially modify the entire series post-Newtonian theory. This might complicate the mapping between a given theory and this parameterization. However, in many cases, it can be shown by essentially doing the parameter estimation that including only the leading order post-Newtonian term is usually sufficient, at least to give an hint of deviations from GR, which is to say, if there is a deviation from GR, and if one is able to capture it through the leading post-Newtonian correction, and if one model is just using the leading post-Newtonian correction, then typically the fact that there are no subleading terms doesn't really sort of jeopardize the possibility to detect deviations from GR. Okay? But it's an important point to keep in mind that for a given theory, there is not just one single parameter that can be introduced here to really obtain the result of the theory, but we have to modify infinite of them depending on the PNO. I mean, potentially infinite if we expand the PN series at infinite order. But anyway, for a given PN order, there will be several parameters for a modified gravity theory, all related to each other. And these, of course, have to be constrained together with the standard orbital parameters that are defined in general. Okay. Let me see. All right. So let me now mention some more corrections that can be used to test the GR at this level. And perhaps among them, one very important one are the multiple models. The idea here is both simple and powerful. because we know that in GR there are uniqueness theorems that tell us that black holes are uniquely determined in terms of mass and spin, and uniquely described in terms of the Kerr matrix.
Professor Pani, sorry to interrupt you.
Sure.
I just wanted to check with the participants if there are any questions, since we hadn't heard for some time. So just checking. Does anyone have any questions? I see a hand raised. Could you please go ahead and ask your question?
Yeah, I just wanted to ask, can you repeat why we need to detect the deviations in the leading order, in the European order?
Sorry, I'm afraid I didn't get the question because my audio is not great. Could you please
Okay,
repeat?
Yes, my question was that I couldn't understand the point why we need to detect the deviations in the leading order of a particular variable, say in phasing or amplitude.
No, so let me see. Is the question related with the leading order terms?
Yeah, leading order terms, European terms, like why we need to detect the leading order thing only. I mean, why couldn't we only have the higher order terms as well?
Okay, so is the question why you need only to introduce deviation to the leading order terms?
Yeah, yes.
Okay, yeah, so yeah, this is not trivial. In fact, it might not always be the case. The argument is essentially the following: that suppose that one has a theory in which, I don't know, there is an alpha naught correction with some power f to, well, let's say to some power. Well, let's write this form. One has correction, that is 1 plus delta alpha v squared plus delta beta v4, etc. When these terms here in the parameterization are totally independent, but maybe for a given theory, delta alpha and delta beta are related, right? Because maybe for a given theory there is just a single coupling constant, that is, say, the new coupling constant of the theory, and therefore these quantities will be fixed once the masses, spins, and the coupling constant of the theory are known. So in principle, in order to have really a one-to-one mapping between the parameterization and the theory, I should include this term and this term, maybe up to, say, second Poisson corrections. The argument is that if I neglect this term, typically, at least if I look in this case at the early spiral phase, possible corrections that I'm missing here because I'm neglecting the term will be captured when I do the parameter estimation by a bias value of this coefficient, but anyway it will be non-zero. So it will be very difficult if the true signal is something that contains both this delta alpha and delta beta to be misinterpreted by a GR signal if I try to recover it just reducing this quantity here. This might not always be the case, especially because it's a statement that depends a lot on the regime where we are looking at. Of course, the closer we look to the merger, the more equally important will be these corrections, and therefore there could be very strong correlations between the parameters. But in certain regimes, this might not be the case. And what is important is that in order to do a null test, namely just check whether there are, something is inconsistent with GR or not, including only the leading order term is usually sufficient. I don't know if this answered the question.
Yeah, so you are basically saying that since the higher order terms are like smaller compared to the leading order terms, hence that like for the inspired regime only, that doesn't contribute that much compared to the leading.
Yeah.
Okay.
So we have one more question from the attendees. So I'm going to allow you to unmute now. Please unmute and ask your question.
Thank you very much for my research. I have a question about the Harry solution. So the one we presented for Gosponet, what about the hair? Is it primary hair or secondary hair? And the second one, is there a way to parameterize Harry solutions in theory agnostic way?
Okay, so I didn't understand the second question. The first one is about the amplitude, right?
Yeah, the first one, it's about the hair in the scalar Gauss-Bonnet. Is it primary hair or secondary hair?
Okay, okay, good. Yeah, so they are both very relevant. I totally missed telling something about the amplitude. I should. For the amplitude, there is a post-Newtonian expansion very similar to the one of the phase, of course with different coefficients, but the philosophy is the same. So we can compute it precisely order by order in the velocity, and in principle also modify it through PPE terms, so parameterized Poisson-Einsteinian terms that go to modify the amplitude coefficient in the post-Newtonian series. This is done, and it should be done every time. It so happened that the phase, that gravitational detectors are more sensitive to the phase differences than to the amplitude, but definitely something that one has to take into account, and also to take into account the amplitude of different modes, which is also an important point. This is for the first question. For the second question, so primary, secondary hair. So for those of you who do not know, so primary hair is really a hair that is totally independent from other parameters. A secondary hair is, for example, a scalar charge that is proportional to the mass, so that in fact does not introduce any new parameter in the theory, in the solution. For quadratic gravity, the simplest black hole solutions that one can think about in scalar, what is called scalar dilaton Gauss-Bonnet gravity, they have secondary hair, meaning that the scalar charge is fixed in terms of the mass and the coupling constant of the theory, but it's not a free parameter. In scalar tensor theories for neutron stars, and also in quadratic gravity in certain theories that allow for what is called spontaneous scalarization, namely there are certain couplings that allow GR solutions to exist, but then also this solution might be unstable, and there is another solution with a scalar charge that is stable. So for solutions with spontaneous scalarization, the situation is a bit tricky, because in that case you have both GR solutions that exist plus a new solution. Typically, the new solution is not does not introduce a new hair, in the sense that there is a continuous family of solutions in which the mass is the same but the scalar charge is different. So also in that case, in a sense, is a secondary hair. But there are also examples of other theories in which the hair is primary. So it's really an extra degrees of freedom, and you can have two black holes with the same masses, same spin, and a different, for example, scalar charge. In the example I was mentioning, is always second hair. Okay, so I want to mention a few things.
Just a question, sorry. Which kind of theories have primary hair for scalar tensor theories?
No, for scalar tensor, I think it's always...
No, when I mean scalar tensor, I mean Hordensky, and even beyond Hordensky, like the most general scalar tensor theory. Is there a hairy solution with primary hair or not?
Yeah. So for the only example on the top of my mind now of sort of primary hair is when there is gravity. It's not even a modified theory. It's gravity coupled to a scalar field, complex scalar field, which can give rise to what are called Kerr black holes with scalar hair. In that case, there is a free parameter that interpolates between a Kerr black hole, standard Kerr black hole vacuum, and then a Kerr black hole with a scalar non-trivial profile around it. There is a free parameter one can adjust to go from the Kerr black hole even to actually the opposite case, which is a boson star, so a scalar condensate without any horizon. And there is a free parameter that can be interpreted as a primary hair.
Okay, thank you very much.
Okay, so I want to, let me see, I will have 5 minutes, but I'll try to be very brief because I want to mention a few things. One is that for curved black holes in GR, there is this beautiful relation. Let me write it properly. See if I wrote it correctly or not. Yeah, with MLR. So there is a beautiful relation due to Gerok and Hansen showing that the mass, these are mass multiple moments, and what are called current multiple moments, satisfy this single very elegant relation. When m is the mass of the space-time, chi is the dimensionless angular momentum. So this tells us, for example, that for a curved black hole, we have m0, which is just the mass, the monopole, m2, which is the quadrupole, and that is proportional to chi squared. We don't have m3, we have m4, proportional to chi to the 4, and so on and so forth. We only have even powers of the multiple. For the current moment, we have S1, which is the spin. Then we have S3 proportional to chi3. We don't have S4, we have S5 proportional to chi5, etc. So there is a very specific way the multiple moments enter the curve solution, and they are all spin induced in the sense that they are proportional to powers of chi. All of this is not true if the black hole solution is not a curved black hole. If it's not a black hole, it's not true anymore. For neutron star, this is also not true, and therefore we can test this relation here, the Noether-theorem relation, through gravitational waves in many ways. One is again the post-Newtonian expansion, because it can be shown. I don't have time now to show it, that M2 enters the waveform to second P-n order. It's actually a simple computation with what I was mentioning before. And therefore, if one is able to measure accurately the 2Pn coefficient in the phase, it is possible to put constraints on M2 and therefore test this formula here. And higher order multiple moments enter the gravitational waveforms to higher order. So the more orders one can constrain, the better this expression can be constrained. So of course, for any other object, so if an object is not a curved black hole, so either is a black hole in modified gravity, or is an object which is not a black hole, whatever, a neutron star, and 2 is not, I mean, would be like M2 curve plus delta M2, so some correct. And of course, there can be moments that are zero by symmetry in curve, like M3 or S2, and they all enter the waveforms at different post-Newtonian order, so they can potentially be constrained by post-Newtonian test the same way I was mentioning. In fact, in the LEGO paper, you can find several constraints at different P-n order of this coefficient that can be translated into constraints on the multiple moment. Let me just mention that so the correction to the quadruple moment can be computed by including in the Lagrangian an interaction pair that is typically called QAB, where this Q is the quadruple moment tensor, plus a term that couples the quadruple moment tensor through this guy, which is the tidal field of the binary. And now, well, I don't have time to enter in any details, and also I think that in Poisson's lecture you will learn more about it. But from these two corrections, the equation of motion for the quadruple moment tells you that at the adiabatic level, the quadrupole moment is proportional to the tidal field through this number here, which is called tidal of number. And it's simple to see that because GAD goes like 1 over R cube, so this is the tidal field, say, of the object 2 acting of object 1, and because the quadrupole moment enters a 2pn order, if we use this relation inside the 2pn correction, it tells you that there is a 5pn term proportional to this lambda. So it is just by summing the 2pn correction coming from the quadrupole with the fact that the quadrupole can be induced by the field, the tidal field of the binary that enters a 3pn order. So these are 5pn corrections. It's in principle small, but this tidal of number, also called tidal deformability, can be quite large, especially if the object is not compact. And is in fact the way the equational state of neutron stars has been constrained by gravitational observation by putting constraints on this deformability. Why it is relevant in the context of test of GR? Because, as you will learn from Eric Poisson's lectures, the tidal of numbers of black holes in GR are 0. So this lambda black hole is exactly 0. And this is not true essentially in any other case. So it's not true for neutron stars, it's not true for black holes in modified gravity, and this is not true if the object is not a black hole. So it's really a property of black holes, of Kerr black holes, so black holes in general relativity, which is again important because if one is able to constrain the 5pn coefficient, one will be able to put an upper bound on this lambda black hole, potentially measure something that is non-zero, and for example, measuring a binary, a compact binary with masses, say, of 10 to 30 or 50 solar masses, so masses that cannot be explained by neutron stars, but measuring a non-zero tidal of number would be a clear indication that something is going beyond our standard paradigm, because in GR there is no expectation that the log number for a system with masses bigger than, say, 2 or 3 solar masses should be non-zero. So these are clear smoking gun of something beyond GR that, if detectable, it's hard because it's very high order. If detectable, of course, will be very, very interesting, potentially groundbreaking. Okay. So I think I will finish here. Tomorrow, before going to the read down, I want to discuss a bit also gravitational propagation test and extrapolarizations, but I think I will do it directly tomorrow at the beginning of the last lecture. Okay, so if you have any questions, let me know.
So Professor Pani, I do have a question. It's a slightly general question. So supposing we had, say, a scenario in which we had a gravitational wave event and we find that, say, one of the post-Newtonian coefficients is deviated. Is it a sufficient condition to claim a deviation from GR, or can we have scenarios which are consistent with GR, but say because of the lack of including them, for example, say you had an accretion disk around a black hole that you've not actually considered, could those things also cause deviations of post-Newtonian parameters?
Yeah, this is a very good question. I was planning to mention a bit environmental effect tomorrow. The short answer is that, well, if something anomalous is detected, of course, this will trigger a lot of independent analysis and trying to test all possible corners that might be wrong. Environmental effects, which essentially means whether the assumption that black holes are in vacuum is wrong, or maybe, as you said, there are accretion disks, or maybe dark matter halos, or any kind of sort of environmental properties that might spoil the waveform. That, in fact, introduced different post-Newtonian corrections, depending on which kind of matter distribution one considers. typically the effect is pretty small. I mean, smaller than the current accuracy of gravitational wave detectors. So that would be hard to explain the anomalous effect. Of course, one might always argue, I don't know, that we don't know very well the environment when these mergers occur. And maybe, I don't know, they occur in a dark matter spike when there is a lot of dark matter, and therefore accretion from dark matter or other effects like gravitational dragging are important. And that will also modify the wave. So that is something for sure that people should then consider very carefully. My impression is that more than this, one should understand waveform systematics, because post-Newtonian theory is valid, strictly speaking, when the velocity is very small, but in fact, the velocity is never small in a merger, and some of these terms are higher Pn coefficient, so they are relevant when velocity is starting becoming relativistic, and therefore the higher the Pn correction, the closer we will be to the coalescence and merger, and therefore the less convergent will be post-Newtonian theory. So this is taken into account also in LIGO test by studying, I will mention it tomorrow, I mean, using full waveforms, is parameasuring a waveform that takes into account everything. The problem is that we have those waveforms essentially only in GR, and in other theories, they are either approximated or phenomenological. So we don't have right now waveforms describing the full parameter down at the same level of accuracy as of GR, and that is a limiting factor. So yeah, to answer the question, I think that if something anomalous is detected, one will need to carefully explore the possibility of waveform systematics, and then possibly do a comparison, like a Bayesian comparison between two theories at the same level, I mean, described by the same level of accuracy in terms of waveforms.
I see. Thank you. Thank you very much. So let me just quickly check if there are any questions. We probably have time for only one more, and I do see a hand raised. So again, could you please unmute and ask your question?
Yeah, thank you. I have just a question. How could we detect hairy black holes? Like, if we want to see, even if it's a secondary hair, but for both cases, when we have still a black hole, like the same geometry as a black hole, as a GR, but non-trivial profile for the scalar field, and the other case where we have a different geometry from GR, so how we could detect them astrophysically?
Okay, yeah, so I'm sorry, I have to apologize because the audio here is really bad. So if I understand properly, so you're asking how to detect possible hair if black holes are not hair black holes, right?
Yes, that's right. How to detect hairy black holes for both cases when we have the same geometry as GR, like stealth black holes, or when we have different solutions completely.
Okay,
like the one you presented.
Yeah, this is a good point. I didn't stress enough. So it is possible, for example, in principle, it is possible that in theories, when there is an O'Hare theorem in place, for example, scalar tensor theories, black hole solutions are the same of GR, but in principle, the dissipative sector of the theory might be different. So maybe we have the same black hole solutions, the geometry is the same, the geodesics are the same, but the way gravitational wave emission is computed is different, and this will change the fluxes and therefore the waveform. This is a possibility that might or might not occur. In scalar tensor theory, it does not occur even if there is not really a theorem. It has been proved up to very high Pn order that there are no corrections even in the dissipative sector. It's sort of understandable because if the black holes are GR and do not have charges, there is no reason why they should emit differently. Okay, and in fact, this has been proved order by order. But there might be other cases, and I can mention the example, for example, of what is called dynamical Transcendent gravity. This is a particular quadratic gravity in which only the parity violating solutions of GR are different. For example, Schwarzschild black holes are solutions also of this theory. Kerr black holes are not. And what happens here is that if you take two non-spinning black holes, two Schwarzschild black holes, they are described by GR, but their dynamics, because the binary is not spherical symmetric, emits gravitational wave differently, and also is described by different geodesic motion. So in that case, that's an example of black holes described by GR, but whose gravitational wave emission is different in that particular theory. Clearly, these theories are the most difficult to constrain because the leading order effect is when the black hole are different. And for example, there is bipolar emission of scalar charges, but nevertheless, it is possible. If there is scalar hair, it's easier because the leading order term is precisely bipolar emission. And in general, for any black hole that is not GR, we expect, for example, quadruple moments, this guy here, to be correct. And so by looking at 2PM terms, we can in principle constrain. These are the main signatures in the spiral. Then tomorrow we will see what happens in the ring down.
Thank you.
Okay, since we are about 10 minutes past the hour, I guess if you have any additional questions, you could ask Professor Pani tomorrow. So we'll thank you once again, Professor Pani, for a very nice lecture, and we look forward to the lecture tomorrow.
Thank you. See you tomorrow.